Okay, hello everyone. So today my talk will be about my latest project called Bochspwn Reloaded, which is about detecting kernel memory disclosure with emulating x86 and Tain't tracking. Or at least that's the official title, because I also came up with a few unofficial ones. The first one could be I got 99 problems, but kernel memory disclosure ain't one. Yeah, which is a modification of a title given by Alex Ionescu 4 years ago here at REcon as well. But even with this modification, I think without it, it would work as well, because kernel memory disclosure often leaks kernel pointers as well. And another one is kernel bleed, because it seems that nowadays everyone wants to have a bleed vulnerability, so I figured that is my best chance to have one as well. So there you go, kernel bleed. And so, yeah, on a serious note, today I will first start talking about the communication between user and kernel mode, what are common pitfalls in modern operating systems. Then I will proceed to talking about Bochspwn Reloaded, how it works in general, what is the basic principle, and how to detect kernel information disclosure using it. Then I will talk about the approaches, results, and exploitation that are system-specific. I tested Windows and Linux in this regard, and then I will just follow up with some future work and conclusions. About myself, I work at Project Zero at Google. I am an active CDF player at Dragon Sector. I'm interested in low-level security stuff, as you can figure. I have a blog and a Twitter if you're interested. The slides will be announced there in a few days, I think. So let's start with the user-to-kernel communication. As you probably know, user applications run independently of other programs in the kernel. Whenever they want to do something in the operating system, they just call into the kernel, and when they do it, the ring-free memory is the data exchange channel that they use. Also registers to a small extent, but that's not really important for us today. So this is the basic graph of how it works. We have the user mode program, which wants to invoke a syscall, so it first writes some input data to the user mode memory, then transfers control execution to the kernel. It reads the input data, performs its logic, then writes the output data, returns the user space, and then the user space program can operate on the output data. It's all very simple and obvious. And what we are interested in today is just the two stages of reading input data in the kernel and writing output data, and actually specifically just the second stage. So yeah, on a more general level, in a perfect world, we can imagine that within the scope of a single system call, each memory unit should be first read from at most once in a secure way, and then after the system calls perform its logic, it should be written to again, but only once in a secure way, and only with data that is intended for user mode. So this is the perfect reality, but you know how life is. So there are like tons of ways to violate all of these assumptions that I listed. I will just quickly go through some of them, because I think they are all interesting ideas of what you can find using system instrumentation. So first of all, of course, you have double fetches. So you can violate the reading from at most once assumption. That was the subject of our original research with Genvail Colwyn 4 years ago. And the possible violation of this is that you can read like twice or several times. And this allows for various bad things to happen, such as buffer overflows, write-what conditions, and stuff like that, depending on how the driver assumes that the data doesn't change in between the reads. And so this has led to over 40 vulnerabilities fixed in Windows. And I also ran Bochspwn, the original one from 4 years ago, just recently, and also found a few more bugs. But yeah, so we wrote a few papers on it. Quite a few bugs were found, some presentations, and a Pony Award. Okay, so but then there are also other things that we can break. For example, the kernel might try to read the data, write the data, but not in a secure way. I mean, normally it's quite obvious that any access to user mode memory should be guarded with a try except block, because the kernel never knows if the address is valid or not before it actually tries to access it. But if it doesn't do it for whatever reason, then this user mode access may lead to an unhandled exception and a system crash as a result. Which leads basically to a local authenticated DOS condition. So it's not very bad, and it's not fixed by Microsoft in bulletins. But if we wanted to find bugs like that using system instrumentation, we should look at the exception handling record generated by Visual C++, and specifically the try-level D word that is inside of it. So how exception handling works here is that, as you can see in the code, an identifier of the exception handler is written to the stack try-level variable in the exception record. Then the write to user memory is performed, and then the try-level is again overwritten with a value of -2, which means that the exception handler is disabled at the time. So at any given point of time, if you access user mode memory, this is how it basically looks like when it comes to the sec chain. So you have fs0, which points to the first exception handler, etc., etc. And if you want to find instances of accesses which are unhandled, then you have to traverse the whole sec chain and see if any try level is positive. If none of them is positive, then it means that there is no exception handler installed, and then you can trigger episode most likely by using this memory access. So I actually also ran this kind of instrumentation with bugs and found a few bugs and documented it on my blog. They are not fixed, so we can still use them to crash Windows. It's just 5, but I think there are more of them if you really want to look deep into the operating system. Okay, so there are also some other things that you can kind of try to detect. For example, there is a global variable in Windows called previous mode, which indicates if the color of the system call is user or kernel. So for example, if previous mode is set to kernel mode, but it's operating on a user mode pointer, then possibly it might be possible that Windows or some other, Windows in this case, gives too much trust to this pointer and doesn't really realize that it's a user mode pointer. Then you have double writes. So for example, you can detect if a kernel within a scope of a single system call writes to a specific memory area more than once. This is also interesting and may indicate some fishy behavior. The question is, why does the kernel do it? Does it not realize that it's a user mode pointer? What is the data that is written before the final write and stuff like that? So this could indicate something interesting. Also, reading after writing is something to think about, because, yeah, why would the kernel actually try to read from a user mode memory after it writes to it? Does it assume that the value doesn't change? What does it write? Yeah. And there are some other heuristics that you can use using system instrumentation. So for example, you can look for user mode accesses with very deep call stacks, which may indicate that also the code doesn't realize that it's really operating on a user mode pointer. You can search for user mode accesses with the first enabled exception handler, which is very high up the call stack, which means that any exception that would be generated at this time would skip over a lot of functions, and this could like leave some dangling state or something like this. Or you could just list all user mode accesses in general, for example, enumerating new attack surface. But the actual subject of this talk is violating this assumption of only writing data that is intended for user mode. So when does it really happen? I mean, there are, like, in general, four places where this happens. Of course, system calls. It happens in almost every system call. Then we have IOCTLs, which are a specific case of system calls. But they have some dedicated output mechanisms. We have user mode callbacks, which are specific to Windows and the Win32K subsystem. And we have exception handling when the kernel builds an exception frame on the user mode stack, for example. So let's look at when can this problem really occur. So we have this easy problem of primitive types. You have an example here of a local variable, which is written to user mode, but it's not initialized if the input value is equal to 0. And yeah, this is one example. Such disclosure, of course, can and will occur, but it's not really so important for us because, first of all, it's not a trivial bug to make. Compilers will see this and will very often warn about it. The leak is very limited. It's like 4 bytes or 8 bytes on maximum, and it may be detected during development because it's often a functional bug. So some very simple testing of the system call that I just showed would catch this. So this is not a really inherent problem, in my opinion, to kernel security, but there are some harder problems that we really have to think about. So in this example, we can see a structure that is being output to user mode. It has 3 fields. 2 of them are filled out by the system call, but the other one is reserved. So by design, it's never filled out, and it's leaked to user mode in this code. Another example here is a union. So we have 2 fields, one D word, one Q word. And in this specific example of a system call, just the smaller field is filled out, which leaves the higher 32 bits uninitialized again. And then we have another problem, which is the padding in struct. So we have a D word followed by a Q word. And even though both of the fields are are initialized, which is fine, and then still the 4 bytes of padding are left like garbage and are still copied to user mode. So yeah, so this is one of the hard problems, and with many fields in structures and fields, it's easy to forget some of them, or as I shown before, it's not set by design. You have holes for data types of different sizes in unions. You have padding holes to align fields in structures. So yeah, it's all pretty messy, and also compilers have very little insight into structures in general. Another example of such problem is fixed size arrays. So here you have an example of a system call that in theory returns the system path. So it uses an array that is fixed in size. It's very long, has like 260 characters, but it only uses a few of them. So the whole rest of this array actually is left uninitialized and also copied to user mode as a whole. And this is also very frequently seen in Windows. So we have many instances of long fixed size buffers for storing paths, names, identifiers, etc. And yeah, as I said, while the container size is fixed and usually pretty long to be able to accommodate all of the possible values, the content length is usually variable, and usually it's much less than the size of the container itself. And additionally, these strings of fixed sizes are frequently parts of structures, which makes it even harder to only copy the relevant part to user mode, because people are just using memcopy with size of as the argument for those. And it may disclose huge portions of uninitialized memory at once. And then we have yet another example of this hard problem, which are arbitrary request sizes. I think this is pretty specific to Windows. So what happens here is that the system call takes the length of the output buffer from user mode and allocates this length on the kernel heap, for example, then only fills out the relevant part of the buffer, but copies it again as a whole to user mode. So this is also pretty bad and leaves a lot of uninitialized memory in the buffer. And yeah, as I said, it's common in Windows with making allocations with the user control sizes and passing them back as a whole. And what's interesting is that it may enable the disclosure from both stack and heap in the same affected code, because Windows often uses an optimization. So it uses a stack buffer for small requests, and it only falls back on pool allocations for larger ones. Yeah, so and it often leads to large leaks with a controlled number of bytes. And what's even worse is that the user can actually choose the number of bytes that are allocated, so he can align the size to be able to collide with some interesting freed objects in the pools and disclose something valuable from there. And there are some also extra factors that contribute to this whole problem. First of all, there is hardly any automatic initialization in Windows or Linux for stack and heap allocations. The exceptions are seen mostly in Linux in the form of the casealloc function, the GFP0 flag, and stuff like that. Also, just a few days ago, Microsoft introduced a new mitigation that clears the buffered IOCTL IO buffers for us, but that's just from a few days ago. And, but in general, the resulting regions from allocations have some leftover garbage bytes in the whole buffer until we initialize it. And even if you look at the documentation for the xallocate pool with tag function in the MSDN, you can see that they are explicitly warning about this problem, that if the buffer is going to be shared with user mode or copied to user mode, it should be initialized in full first, preferably using a memset. Another extra factor is that there are no visible consequences of this problem. So, and this is like a problem with C and C++ in a way, because it doesn't make it easy to copy data securely between different security domains. But the other thing is that there is really hardly any punishment. So if a kernel discloses a few bytes here and there, nothing will ever happen, nothing will ever crash, and no one will ever know until probably now. And this also means that if a kernel developer makes this bug, he won't, they won't find out by accident during normal work if they don't look for this kind of bug. And yet another factor is that it might not be so easy to catch this bug in the wild while doing regular work, because of the fact that even though a system call might return some uninitialized bytes, they could be, stripped off by the user mode API that is actually called by the user mode program. So the program could maybe never even see the data that is leaked from kernel mode. So when it comes to the severity considerations of this bug, these are just like local info leaks, obviously. There is no memory corruption involved. There is no remote exploitation kind of involved by nature. The actual severity of these bugs depend on what specific data we manage to leak out of the kernel, but on the upside, we don't have to worry about system stability. We can just reproduce these bugs forever and try to leak as much data as we want and try to collide with something interesting. I think that these bugs are mostly just useful as a single link in a local privilege escalation exploit chain, especially nowadays, given the fact that Microsoft invests and also Linux invests so much time and effort into KSLR and it being effective. And one real-life example of this kind of issue being used in an LPE chain was in a hacking team dump in July 2012. So they used a pool memory disclosure to leak the base address of win32k.sys. And it turned out that another member of Project Zero also found this bug and collided. So here you can see the title in our Project Zero bug tracker. So the benefits of the stack or heap disclosure depends on what the type of the memory being disclosed is. When it comes to the stack disclosures, we have a consistent, immediately useful values, but it's very limited in variety and potential. Like, for example, we can get very easily the addresses of the kernel stack because there is a lot of same frame buffers or stack frames and stuff like that. We get addresses to heaps because they are also stored on the stack. We get return addresses, which means pointers to executable images. We get stack cookies. Also, any other kind of syscall specific data that was being used by the syscall executed before the one that leaks data. And we also, interestingly, can potentially get data of interrupt handlers if the interrupt handler was executed on the same stack that we are leaking just before we have exploited the vulnerability. But when it comes to the heap, it's a little bit different. The memory that we are leaking is a little bit obvious, but it has more potential to actually leak something more interesting. So by design, we get addresses of the heap, potentially executable images, but in reality, we could possibly get like data of any active kernel module that creates an allocation in the kernel and then frees it at the right moment. So I also wanted to talk a little bit about the prior work in Windows and Linux. When it comes to Windows, there hasn't been too much prior work. So we have this Project Zero issue from July 2015. Then we have a presentation by the Wandering Glitch from last year called Leaking Windows Kernel Pointers, where he discussed 8 kernel uninitialized memory disclosures that were fixed 2 years ago. Then we have this presentation from Consequest this year, when a few researchers kind of hinted that there could be some information leaks in Win32k in the implementation of the user mode callbacks, but they didn't really give any specific details. And also there is an article from just 3 days ago by some Chinese researchers from Iceword Lab, where they also described something very similar to Bochspwn, but a little bit more limited. So they used this to find 5 bugs that were also fixed 3 days ago in the Patch Tuesday. So not too much work being there in Windows in the last years. It's getting some attention right now. I don't know why exactly right now, but yeah, people are getting interested in this subject. But when it comes to Linux, it's a little bit better. So this project was already thought about in 2010 when Dan Rosenberg had the most impact, I think. He killed like more than 20 info leaks in various subsystems. He also presented this work with John Oberheide in like 6 years ago. So there are also a lot of patches by other various security researchers which found instances of this bug. Yeah, here you can see a few names. So the problem in general seems to be much better solved and much better thought about in Linux than it is on Windows. Okay, so let's talk a little bit about the Bochspwn reloaded design and how to find these bugs. So when it comes to Box itself, as you probably already know, it's an emulator for the x86 and x64 architecture. It has a CPU emulator and implementation of all of the basic peripherals. So basically, it's just a whole emulated computer that you can run operating systems on. It's written in C++. It's developed by Intel, which means that it has support for all of the latest CPU features you can imagine, all of the extensions and stuff like that. It correctly hosts all common operating systems. Myself, I just tested Windows and Linux and didn't have any problems at all with that. And what's the best for us is that it has a very extensive instrumentation API. So when it comes to its performance, this is the short story. This screenshot means that at the time when it was taken, the emulator was executing at 38 million instructions per second. So that's not very impressive. When it comes to the long story, if we don't have any instrumentation at all and just run the vanilla box, we get a performance of around 80 to 100 million of instructions per second, which is kind of sufficient to boot up an operating system in less than 5 minutes, so it's not so bad. And after we actually boot up, the environment is fairly responsive, so we can like move around with the mouse, we can start my computer in 10 seconds, stuff like that. So it's not so bad. But when we do actually add some instrumentation, it becomes worse. So the performance in the case of Bochspwn Reloaded dropped to around 30 to 40 million instructions per second. But I think that's still acceptable for research purposes because we're not really that much limited in time and we have to wait for the results for a week. That's fine for us anyway still. So it's workable, I would say. When it comes to the instrumentation support, as I said, it's really great. So we have these BX floor instr macros, and a lot of them, which we can use to hook into various events that are going on during emulation. So we can hook into initialization, shutdown, before and after an instruction is executed, before and after memory access is performed and stuff like that. So we can really learn about a lot of things that are going inside of the system. And this enables us to develop virtually any logic that we want to have for, like examining the state of the operating system or even changing how it works in different ways. So here you can see the list of all of the macros that are available, and the underlined ones are the ones that I used for Bochspwn Reloaded. So it's just 5 of them for initialization, exiting the virtual machine, before and after executing an instruction, and for every linear access that is performed by the operating system. And so the core logic of Bochspwn is basically just to have Tain't tracking for the entire kernel address space. And for this, we have to be able specifically to set Tain't on every new allocation that is going on, both on the stack and the heap, removing Tain't on free on the heap, of course, propagating Tain't in the memory once it is copied between 2 different regions. And what's most important in all of this is detecting copying of the tainted memory back to user mode. This is the core functionality, but we also want to have it to be, quite convenient for us. So we also wanted to keep track of all of the kernel modules that are loaded in the operating system, so be able to symbolize the stack traces. We want to be able to read the stack traces in the first place. As I said, symbolizing call stacks. And what's also nice is that we could want to break into the kernel debugger once memory disclosure is actually taking place. So here we have the representation of the shadow memory, which stores all of the Tain't information that we have. So you can see we have the guest memory. Half of it, in case of Windows at least, is taken by the kernel land memory. And so all of it has basically a linear representation of the shadow memory. And each item in the shadow memory stores several types of data, most importantly the Tain't information, but also the allocation size that this memory unit belongs to, the base address of the allocation, where the allocation was made in the kernel, what were the flags specified in the allocator, and stuff like that. Currently Bochspwn supports only 32-bit guest systems because of the fact that we just have like a large array that is linear to the size of the kernel address space. Some of the information is stored at 1 byte granularity, some at 8 byte granularity. And as I showed, we have some extra metadata, which is not really important for just tainting, but also for figuring out where the allocation was made, what the bug is, and stuff like that. So basically, as you can see, for every gigabyte of memory of the guest operating system, we have 3 gigabytes of shadow memory. So for Windows, it's 6 gigabytes in total. Right now, for Linux, it's 3 gigabytes. So if you have just the normal amount of RAM in your computer, you can run this instrumentation without any problems. Another thing that I implemented in this project is something called double tainting. So basically, for every time a region is tainted in our shadow memory, we also pad all of the resulting allocated guest memory with some special byte. In my case, it was AA for the heap and BB for stack areas. So this gives us a couple of advantages. First of all, we may actually see some bugs which are not related to just memory leaks, but like regular usage of uninitialized memory. It provides us evidence that the bug indicated by shadow memory is actually real, because we can see that the bytes that were set during allocation are still set to this original value at the time of the leak. And thanks to this, it also eliminates almost all false positives that we can think of. When it comes to setting taint on the stack, this is actually pretty simple and pretty cross-platform. So what we do in our instrumentation is that we just detect all of the instructions that modify the ESP register, which means add ESP, sub ESP, and ESP pretty much. And after execution of the instruction, we check if ESP after executing this instruction was decreased. And if that is the case, then we just set taint on the whole memory region that was created by subtracting ESP. This, of course, relies on the fact that the guests have to behave properly and never reference ESP with a negative offset and stuff like that. But it turns out that both Windows and Linux do, and they don't have any problems with that. When it comes to setting taint on a heap and pools, as like this is actually very system specific. It requires us to hook into the allocator of the operating system at somehow know both the allocated address and the request that led to it, meaning the size, flags, origin, etc. at the same time. And once we have this information, we just, again, set the taint on the whole region that was allocated. Then we remove taint on heap free, which means we have to, again, break on the free function or functions possibly, look up what the allocation size was, and free the whole memory region again in our shadow memory. And now we come to the hardest problem of all, which is taint propagation, because we somehow have to detect data transfers between memory. And so this is why I said in the abstract of the talk that the taint tracking is rudimentary, because we only actually propagate taint for the one instruction, which is mov-sb, mov-sd with the rep prefix, which means that we know about all of the memcopy calls, both like a regular function calls and also the inline versions. And what this gives us is that we have both the source and the destination address at the same time set in the ESI and EDI registers. So we can very conveniently move taint from one place to another. And this is actually quite good enough for us, because we mostly care about copies of large memory blobs. Anyway, as I said before, basic types are not so much of a problem. The bigger one are the larger structures, arrays, and stuff like that. So this is basically just the best effort approach. Could be probably improved, but it would require adding, I think, a lot of code in the instrumentation, and benefit would be arguably quite little. So then, if the memory access that we are instrumenting is not a result of a rep mov-sb or rep mov-sd instruction, then we also perform some logic. So if the instruction is writing, we just clear the taint on the memory area, meaning we're marking it as initialized. And if the instruction is reading from memory, we're checking the taint of the memory region. So if the shadow memory indicates that it's an initialized read, we verify with guest memory to check if the bytes in the guest itself are still the padding ones. And if there is a mismatch for some reason, then we also clear the taint. Otherwise, we have a bug that we can report possibly if we are running in strict mode, or ignore it otherwise. But when it comes to the bug detection itself, well, this is pretty simple. It's also activated on the rep mov-sb, rep mov-sd instruction, with the condition that ESI is kernel mode and EDI, so the destination is in user mode. If we detect that the memory area is tainted at this point, then we just report a bug again. So this is the basic principle, and now we can talk about running it on some real systems, starting with Windows. So the first OS-specific thing is tainting pool allocations and untainting them. So we have to learn about the allocator. In Windows, we have several allocator functions. They have all of them have the same prefix of xallocate pool, but now they have different suffixes. But the nice thing is that they eventually all call into a single one called xallocate pool with tag, which has a std calling convention, which has the nice property that all of the arguments for this function are on the stack, and the return value is in EAX. So when this function actually returns, we have all of the information about the request and the result of the request at the same time. And it's very similar for untainting free allocations, but we just have to hook into the x3 pool function. So yeah, basically this is how it looks like. We have some callers of the allocators of the different functions. All of them eventually end up in xallocate pool with tag. So we just hook into this single read instruction here, and we read all of the information that we're interested in at this very moment. And that's about it. And the same for freeing. So here we have fewer functions, but they still, all of them eventually call into x3 pool with tag. And then we can, in the function prolog, we can just read the address of the freed region and untaint the memory region. There are some slight problems or some slight things that you have to keep in mind. For example, there are some dedicated allocators in Win32k, such as this alloc free temp buffer, which has a kind of a look-aside, a single memory region that it tries to return before making an actual allocation. And so if you want to get rid of it and also have this region covered by your instrumentation and tainting, you have to patch it out to make it always create an allocation. And so when it comes to propagating taint in Windows itself and detecting bugs, our logic of only instrumenting repmov_sd is actually quite good, because the standalone memcopy function used by the kernel uses this repmov instruction. Yeah, and all instances of memcopy, have the same signature. So even though there are some optimizations in memcopy which use registers instead of the repmovs function, you can also just patch them out automatically. So that's pretty easy in Windows, and we don't have to make any changes to our logic that I talked about before. And here we have a small animation. I don't know how well you can see it, but basically, that's just 40 minutes of Windows runtime from boot to starting some unit tests with a 20-second interval. And here you have the whole address space on a 1024 by 512 pixels. Each pixel is a single memory page. So we can see the stack pages in green and the pool pages in red. So yeah, you can kind of visualize the state of the kernel address space. You can see how much address space is actually consumed, and see some other interesting patterns. So this is for Windows 7. This is for Windows 10. It's a little bit longer. It's like 2 hours of runtime with 60-second interval, also booting up and starting some React OS tests. So eventually you can see, for example, that it's taking much more memory than Windows 7 does. Anyway, when it comes to some other implementational details, such as keeping track of processes and threads, this is basically just about traversing a kernel linked list, and it's the same as in the original Bochspwn research, so I will not talk about it today. You can look it up. And the same thing for keeping track of loaded kernel modules. It's pretty simple, technically. So here you can see an example of a Bochspwn reloaded report. So you have the address that was referenced, the name of the process, the instruction, which is obviously here repmov_sd. This is a leak from the stack, so the pool allocation is not recognized, and you can see that the shadow bytes are the 3 last shadow bytes from the 4 bytes are set to FF, which means this is a tainted region, and this is confirmed by the fact that the guest bytes, the last 3 ones, are actually set to BB, which are the padding bytes. And then we have a very nice struct trace, which shows us where the bug actually happened. So this was all very nice and very verbose, but sometimes this is not actually enough to be able to reproduce the bug very easily and find out what it is. Especially for things like IOCTLs and other complex cases where you have a very long call stack, like 20 levels deep, and it's really hard to figure out how execution got there and what is actually being returned to user mode. So the solution for this is to attach WinDBG to the emulated guest kernel. And this is not very hard because Box actually has support for redirecting comports to Windows pipe. Of course, this is slow, but working on this project makes you used to this kind of slowness. And so just attaching a debugger is, of course, not enough because we still don't know what is going on at the specific time that the info leak is taking place. So My idea was to, after logging the bug into a file, actually injecting an int3 instruction in the emulator directly after the instruction that was leaking memory to user mode, which causes WinDBG to stop at that instruction, and we just have everything that we need to investigate what the issue is. And I personally think that attaching a kernel debugger to an operating system that is being actively emulated by a C++ project is quite magical. At least that's what it feels to me. That's basically how it looks like. So we have the box window with the live operating system, and next to it we have the kernel debugger, which can do whatever it wants. So yeah, we can check the context, we can examine handles, see what the memory is at a specific address and stuff like that. So when it comes to the testing that I performed, first of all, I ran this project both on Windows 7 and on Windows 10. What I did on those systems is that I, of course, booted them up, started a few default applications, generated some network traffic, and ran so-called ReactOS unit tests, which are just a bunch of tests for different Windows APIs. So I would say this is quite a good way to actually generate some nice Windows kernel code coverage. And we also used this for the Bochspwn from 2013, but since then, this set of unit tests very much improved since then. So it's even better now. But in general, I would say that code coverage in the kernel is still a very major roadblock for the effective usage of this kind of instrumentation. So improvements are always very welcome. So yeah, now let's look at the results. The results are basically just summed up here. So these are like 3 months of patch Tuesdays. 90% of the bugs are from 3 days ago, so from the June patch Tuesday. Yeah, that pretty much sums it up. So we have 29 vulnerabilities fixed so far, as I said, mostly in June. Here you can see the division by the type of memory that was being leaked. So we have 12 pool memory leaks and 17 stack memory leaks. This is a short summary. I probably can't read too much from the screen, but what's interesting is that the bugs were found pretty much in all of the components in the kernel, or most of them that you can imagine. So we have bugs in the core kernel, the anti-image, Win32k, some kernel drivers such as volume manager, partition manager, and their respective IOCTLs, stuff like that. The reasons are also very diverse. So we have, structure alignments, structural size miscalculation, alignment of Unicode strings, basically all of the things that I mentioned before. And the number of bytes that were leaked is also very, very varied. So it varies from a single byte to 6 kilobytes in one specific case. So a lot of memory was being leaked there. And then you also have the summary of the stack disclosures. All of these bugs will be open in the Project Zero bug tracker, so you will be able to see the actual details and dig into these bugs if you're interested in that. So once I found all of these bugs, I somehow had to find a way to reproduce them. First of all, let's start with the pool reproduction. I wanted to reproduce every bug, not just in the Bochspwn environment, but also in a separate virtual machine to be able to prove that this is actually a real bug. So what we have to do to reproduce this pool info leaks is that we have to find out which driver is making the allocation that is being leaked to user mode, which is very easy because we already have this information thanks to our metadata in Bochspwn. Then we enable special pools for that module, reboot, and then start the POC twice, make it dump all of the memory that was leaked, and then we can just observe the bytes that are being leaked, that they are changing in between the two runs. So this is how it looks if we start a POC for the volume disk extends vulnerability. One time when we run it, we get these 39 padding bytes inserted by special pools, and when we run it again, we can see that these 8 bytes differ, so then it's obvious which bytes are actually being leaked here. Yeah, about stack info leak reproduction, that's actually a little bit more of a problem because there is no official or documented way of padding all kernel stack allocations with marker bytes, so we have to figure out how to do it ourselves. And because also, in a typical scenario, it may not be obvious which bytes are being leaked if we just dump them to test it out, because, these bytes in a typical scenario may be very non-interesting, such as being just zeros, or even if they are interesting in our environment, when we send it to Microsoft, they might not be able to reproduce the same effect. So we actually want to have something reliable. yeah, for the reasons that I mentioned. And what we can do in this case is that we can use kind of a technique called stack spraying. So in Windows, there are a number of primitives which you can use to fill the kernel stack with controlled data. Thanks to the optimizations that the kernel uses local kernel stack buffers for smaller requests and only performs a pull allocation for larger ones. And how we can identify candidates for such primitives is that we can just look for NT functions with large stack frames in IDA. And that's it. My favorite function to do it is map user physical pages. It lets you spray up to 4 kilobytes of the kernel stack on x86 and 8 kilobytes on x64, so that's quite a lot. And this method was actually documented on my blog 6 years ago. So this is how it looks like. Basically, first of all, we just spray the kernel stack with one of the functions that we find with an easily recognizable pattern, and then directly after that, we just trigger the bug. The kernel code initializes some of the fields, but leaves the other ones uninitialized, and then copies it back to user mode, and then we can observe the padding bytes that we inserted ourselves at the right offset. So this is an example of that. A POC for one of the issues, and here you can clearly see that the 8 bytes at the end of the output are being leaked and are being initialized here. And a quick digression from all of this is that since this method works for reproducing bugs, it could be also used for finding new bugs. And so the idea for that would be just to enable special pools for all the kernel modules that we can think of, and then also use kernel stack spraying. Invoke the tested system call twice, pre-spraying the kernel stack with 2 different bytes, and then compare the output of these system calls in search of repeated patterns of differing bytes at common offsets. So this was my idea of how to find some perhaps new bytes, and I found a perfect candidate of a family of system calls that you can do it with. So there's a family of system calls called anti-query information. There's like maybe 10 of these functions, which basically are just returning some information for a specific kind of object that we generated in kernel mode. And they all have very common definition of the function. So we have a handle to the object, we have the information class, which is an enum of what we actually want to request about the object, and we have a pointer to our buffer in user mode, the length of the buffer, and the pointer where the return length is returned. So what we can do is just we can create a handle to the specific object type, and we can just kind of brute force the remaining 2 things, the information class and the information length. And for every successful call, we can investigate the output buffer and see if there are any leaked bytes there. And this was a fruitful idea for me. So once I found the first bug found by Bochspwn in one of the anti-query information functions or system calls, after I did this testing, I found like 5 more bugs. So that was a good idea. Okay, so I have some demos. It's hard to make InfoLeak demos very visually attractive, but I've done my best to do it. So let's see if they work. We have a Windows 10 here. So yeah. I have a few POCs for the pools and the stack. So what you can see here is that, you have the leaked bytes here listed like printed in hex. The green ones are just zeros, so non-interesting leaked bytes, and the red ones that, I don't know how well you can see them, but they are the leaked bytes. And then we also have a simple heuristic for detecting kernel mode addresses that are being leaked here. So, I have an automatic refresh function here. So you can see that a lot of kernel addresses are leaked, and perhaps some kernel pool tags as well, and sometimes some ASCII strings. So I also have a kernel debugger attached here, so we can verify that the addresses that are being leaked are actually valid addresses. I hope at least that they will. So let's see what happens. Yeah. Yeah, that's a valid address. We can also use the pool extension to actually be able to see what the because yeah, as you can see here, that's a page pool allocation made by GDI. So I won't show all of the demos that are pretty much very similar. Of course, because of the fact that they are different vulnerabilities, that they have different sizes of the leaks. Here we have a vulnerability in anti-trace control. So we can also refresh it a few times. You are able to see some strings here, such as add API and stuff like that. So yeah, you can basically just indefinitely try to leak data using these vulnerabilities, trying to read something interesting from the kernel. So these are the pool leaks, and as you can see here, they are, the output values that you can see here are changing pretty much very often here. I would hope so, at least. It usually happens. But if we try to look at the stack disclosures, you can see that this is a little bit different. So for example, we have this vulnerability, which I think leaks around 150 bytes. It should start soon, I hope. And so then after a while, the stack doesn't really change that much, because that there isn't really too much going on in between the different leaks on the stack of the process, so we just get the same result. And as you can see from a large info leak from the stack, we also get a lot of addresses, and I bet most of these addresses are either from executable images or from stacks or from pools. So you get a lot of information that you can use for a local privilege escalation. So yeah, that's the demo. And now, another demo that I wanted to show you is about sniffing hardware activity. So it turns out that on Windows 7, hardware interrupt handlers operate on the same kernel stack, the currently active thread. And these handlers may leave some interesting traces of data on this stack, right? So, for example, some characteristics of actions performed by other users. And, normally this wouldn't very frequently happen because our thread, like any user application thread, is not taking too much CPU time. But of course, we can use something called CPU time spraying, which is just, an infinite loop, pretty much. And so, yeah, you can see how it works. You just have a thread which consumes like a lot of CPU time, basically the whole thread quantum that it can, and it leaves very little space for the other threads that are executing in the system. So this is what it looks like in Task Manager. Yeah, just 99% of time is taken by our single application here. And the good thing about this is that then the interrupts start to occur within the context of our thread. Here in this example, we have like 6 interrupts, and 5 of them occurred within the execution context of our thread that we're controlling. So the exploitation algorithm for that would be to clear the kernel stack first, meaning padding with 0 with a stack spraying primitive that I talked about before. Then try to consume some number of CPU cycles, which is very simple. We just run a very long loop. We just disclosed the kernel stack memory with our vulnerability, and eventually analyze the data to see if there are any patterns that we can recognize to find out about some system activity. And so the question about what interrupt should we target is quite simple, at least for VirtualBox. So we have this interrupt that handles keyboard presses, which is good enough for us. And this routine for handling these key presses actually saves the scan code on the stack. So that looks very promising. And it is very promising until you actually try to debug all of this and see how it performs on the real system. And it turns out that even the scan code is actually saved on the stack. It is quickly overwritten by some HAL functions, so it cannot be read back, unfortunately. But still, we can recognize some patterns on the kernel stack that indicate not which exactly key was pressed, but that the key was pressed at all. So yeah, we can see a demo for that on Windows 7 with just a single CPU. Yeah, this is how it looks, and hopefully it will look the same here in our test. So we have this keylogger here, and every time I am pressing some keys, it is showing the key presses, and the colors of this indicate the time from the key press to the key press before. So, maybe you could somehow try to figure out what the user is pressing if you know that they are using, for example, English alphabet, or English dictionary, and are typing something specific. So you can see it here. We can also do it like this, and you know, try to look out or switch user and see that even keystrokes in WinLogon are also detected by this keylogger. So it knows about all of the key presses in the whole operating system this way. I'm glad it worked. Okay. So for a quick summary, yeah, it seems that the problems was kind of not very much examined in the past, and not too many people have thought about it, with a few exceptions. And of course, that is quite natural because it's quite invisible and it's non-obvious. So you really have to think about what can go wrong in order to be able to figure that this bug even exists. And unfortunately, it's quite a fundamental issue which is trivial to overlook, but very difficult to get right in the code. Windows itself has a very loose approach to the data transfer between the kernel and the user, and the results of this research perhaps could be just the tip of an iceberg. There could be more instances of the bugs lurking in the code base, because there are like hundreds of memcopy calls in the kernel of Windows to user mode, and every one of them could be basically a potential disclosure. Especially the cases where the size of the memcopy is user controlled, but the amount of data that is being copied is fixed or otherwise limited. When it comes to mitigation ideas, there are some fully bug-proof ideas. For example, just mem-setting all of the stack and pool allocations when they are made. Of course, this would be the perfect solution. It would make the problem go away because there would be no uninitialized data anymore. It would be probably quite easily implemented, but the overhead could be too large, I suppose. And also, it wouldn't make so much sense because most of the kernel allocations don't end up copied into user mode anyway, so it would be a little bit of an overkill. But this is also a tweet from, I think, yesterday. So Microsoft is actually actively working on this. You can see that even though they don't memset all of the allocations, they started memsetting some generic classes of them. In this case, the buffer that is provided to the IOCTL handler for buffered IO IOCTL type. So this already kills quite a large part of these kind of vulnerabilities. So kudos to them. Some more realistic types of mitigations could be to implement something that is already seen in Linux called a PAX memory stack leak option, which clears the whole stack in between system calls, which prevents leaking data between the system calls, which I think is the majority of cases. They could also add a new allocator that just clears the returned memory region already. Doesn't make the user do it, but they could just do it by themselves by adding a new functions for that. And yeah, they could just somehow try to detect which allocations actually end up copied to user mode and clear only those, either automatically or just by manually adding memsets for all of those cases. And you know, being Microsoft and having the source code of Windows, they can really do a lot of interesting stuff because they have access to a much more semantic information than I do. So for example, they could implement taint propagation better than I. They could have more code coverage because I imagine they have definitely more tests for generating this coverage that I have. And they can use static analysis to actually guide dynamic approaches and vice versa. So yeah. Also, interestingly, Bochspwn can also be used not just for detecting info leaks, but also regular use of uninitialized memory. But the results, at least for Windows, are much harder to triage because there are lots of false positives. And because of the fact that we don't have the source code, it's really hard to figure out if a bug is really a bug and what the severity of the bug is. So yeah, and another note is that leaking sensitive data from the pool disclosures seems like a subject that could be still researched because I didn't really dig too much into it, and it could be interesting. So we still have a little bit of time. I will try to make it quick and talk about Linux a bit. So in Linux, when it comes to tainting allocations, it's much more complicated for many reasons. We have more allocators, kmalloc, vmalloc, kmemcache alloc. They have different declarations. They pass arguments via registers and not via the stack, which makes it all more complicated. Kmemcaches have allocation sizes specified not during making the allocation, but during the creation of the cache. They have something called constructors, which initialize, like kind of pre-initialized memory allocations. for the color and stuff like that. So it's much more complicated. Here is a list of allocators that exist for kmalloc family and kmemcache alloc family. This is not all documented functions, but these are the functions that actually exist in the Linux kernel internally that we have to take into account. And then we have some more functions for the vmalloc family. Of course, some of these functions actually call into each other, but still, in order to cover, I think, most or all of the allocations, I have to hook into 7 of them and the corresponding free routines as well. Then we have this problem of passing arguments through registers, which means that we cannot just hook into a single instruction, the ret instruction. We have to hook into the kernel twice, first when the allocator is called, and then when the allocator returns, in order to be able to capture both informations. So this is how it looks like here. We hook into the first instruction of the function to save the size and the flags of the allocation request, and then again we have to hook into all of the return instructions to be able to set the taint based on the allocation address. Then we have the kmemcache create and alloc functions, which is a dedicated mechanism for quick allocation of objects that have a fixed size. So we have to do a lot of additional work to make this work as well. When it comes to propagating taint, it's quite convenient actually, because we can configure a lot of the kernel behavior using just configuration flags. So this combination of 2 flags make all of the memcopy calls actually compile into the convenient rep movsb and sd instructions. And here you again can see how the memory taint layout works in Ubuntu 16.04. It's not very visible, but pretty much most of the allocations are heap allocations, and the basic conclusion is that it takes much less memory than Windows does. But it's also quite obvious because of the fact that the Ubuntu that I tested was just a server edition, so it just had a simple console and no UI. Then we have some other useful config options for enabling debugging symbols, configuring the user kernel memory split, disabling kernel ASLR and stuff like that, basically just to make everything work smoothly and conveniently for us. Then we have to set another flag in order to make the copy to user function use the rep movsb and sd instruction. It's also pretty simple. The bigger problem that we have is that in Linux there is a special function for actually copying basic types back to user mode, and it doesn't use memcopies, so normally we wouldn't really be able to capture any of those reads and writes, and we're really interested in them as well. And it's very difficult to actually be able to modify this macro to use rep movsb or some other kind of this instruction, because the constructs that are passed to this macro are very different in nature. They are constants, variables, structure fields, function return values, and stuff like that. So what I did instead is that I modified the Linux kernel in this way. I added 2 instructions before and after evaluating the expression that is being copied to user mode. So I inserted prefetch 1 and prefetch 2 instructions, which are responsible for kind of enabling and disabling something I called strict mode, which is a mode in which Bochspwn reports all bugs and not just info leaks. So I could do it because normally the prefetch instructions in Box are effectively nobs, so they don't do anything. So I can just reuse them as markers in the code or hypercalls. And in between these 2 instructions, as I said, Bochspwn would just report all of the uninitialized reads. And this has resulted in adding over 300 such constructs in the VM Linux image. So here you can see how it works in IDA. We have these 2 instructions, prefetch 1, prefetch 2, and in between them we have the evaluation of the expression and all of the reads that have the same ESP. So the marked areas are basically sanitized and detected by Bochspwn here. Then we have some more stuff that we have to do that is very similar to Bochspwn from 4 years ago, such as keeping track of modules, some symbolization and stuff like that. We have the example report of Bochspwn on Linux, which is also very similar, but we just have Linux symbols pretty much here and Linux function names. I also used the kernel debugging feature, which was also very convenient for investigating all of the internal system state. When it comes to the testing that I performed, I ran this all on Ubuntu 16.10, 32-bit, and I did also some simple things like booting the system up, logging via SSH, starting a few command line programs, reading from some sudo files, running the unit tests called Linux test projects, and then running some system call fuzzers called Trinity, and I know this. I could also possibly use the syscaller fuzzer, because it sounds like a perfect fit, but unfortunately right now I only support 32-bit mode and it only works on 64-bit mode, so it's not compatible at the moment. As for the results, it's not as good as on Windows. It was just one single minor bug, which is a disclosure of 7 uninitialized kernel stack bytes in the handling of one IOCTL in a device that is only accessible to root. So yeah, it's not very impressive. I discovered this issue around April 20th, and I was just about to report it a few days later, but then when I was looking through commits, turns out that 7 days later, someone else fixed it. So, you know, they are quite fast, I guess. So since I didn't have any good results with the normal logic of Bochspwn, I decided to enable global strict mode and try to analyze all of the uninitialized reads that I can find in the kernel, not only those that are actually copied to user mode. And in Linux, it's easier to triage this kind of report because we can look at the source code and actually see what the problem is or isn't and understand the underlying logic. So that's what I did. And I had a little bit more luck there, so I found a few bugs. Most of them were not really that important, just some small comparisons with specific constants and stuff like that. Most of them were on the stack, some of them were on the heap. And also, interestingly, some of them were being found externally at the very moment that I was finding them as well. Most of them are fixed already, but not all of them. The only actually interesting bug I found was a user mode memory disclosure in the NFC sockets that is in the top here. It's still not fixed, even though it was reported. So that's the only kind of semi-severe bug. Yeah, so the results are pretty okay, I would say, even though like most of the bugs, for example, allow to answer a question of, is an uninitialized byte on the kernel stack equal to 0? So yeah, it's not that interesting from a security perspective, even though it's still a bug and it still was fixed in Linux. There are some false positives, but it's not so bad, and sometimes there are just true positives that are just working as intended. For example, when an uninitialized value is just ended bitwise by 0, so that's just working as intended. But it was a good validation that this approach works, and you can actually also just discover normal use of uninitialized memory in the kernel with this approach. There is a project called Kernel Memory Sanitizer, which is a project that is currently under development by Alexander Potapenko. And this is the right approach for Linux to find this kind of bugs. It's a runtime instrumentation added at compile time that detects use of uninitialized memory. It has much better support for Tain't propagation because of the fact that they have access to the source code. And it's basically a twin project of kernel address sanitizer, memory address sanitizer, and all of the other sanitizers that you know from both user mode and kernel mode. So this project is the actual way to deal with these problems in Linux. But since I already had Bochspwn for Windows working, I wanted to try it out on Linux and find some bugs. So the conclusions for Linux are that the Linux community has been on top of this problem for the last few years. There isn't apparently too much to be found there, even though I had my hopes up for quite some times. And even when the bugs show up, they are rather short-lived, as you could see. Like I could only enjoy my small bug for 1 week, and that's it. And yeah, I think that most remaining bugs should be swept off by KMSAN in the very near future. So when it comes to future work and what's left to do, there are quite a few things. First of all, I would like to run some more iterations of this on Windows, particularly try to actually get a better understanding of some of the uninitialized reads that are not direct kernel memory disclosures, and run Bochspwn in strict mode. Also, of course, I have to look into improving code coverage, because the better the code coverage, the more bugs we can find, obviously. And it's basically a never-ending story. I can think of ways to improve the taint propagation logic beyond repmov-s, and you know, while still having a good trade-off between speed and the number of bugs that I found. And one important thing is that perhaps 64-bit guess should be also supported, because it opens a few more doors for bugs, for example, which are related to structure padding, more coverage, and stuff like that. Then there are some more approaches that you can think about for Bochspwn, like taintless approaches, where you don't store any taint at all. You just poison the stack and heap allocations with magic baits, and then investigate all of the writes to user mode memory and see which writes contain these bytes, and then try to analyze those reports. Or you could generalize this approach and run more than one, just for example, 2 sessions with different marker bytes, and then if there is a location in the code which for every write, it has the respective padding bytes at a specific offset, it also means that that's a bug. And this could, in some part, address the problem of the non-ideal taint propagation that we have right now. Another crazy idea would be to recompile, for example, the Linux kernel or binary write the Windows kernel to, you know, have all of the kernel data transfers performed using mov-s instructions, which would make Box know about all of the data transfers and not just memcopy. We could maybe try to apply this concept to other data sinks, which are not just user mode memory, but for example, outgoing network traffic or the output files saved by applications. Or even apply this whole idea to other security domains, such as inter-process communication for sandboxes or virtualization. There is a lot of things this could be probably applied to. So Bochspwn is not dead. Thank you for listening to me, and I can answer probably questions now or maybe later. Are there any questions? There is one at the back, I think.
My question is pretty simple. You said that you have sprayed the stack of Windows kernels. I'm curious about how. I mean, you did it manually, right?
Spray the stack of the Windows kernel.
Exactly.
Yeah. I mean, there are a couple of functions, a couple of system calls which just have like enormous buffers that just copy the data that is provided by user mode into those buffers. And so you can use these functions to just spray, meaning like fill the kernel stack with controlled data this way. So the one system call that I mentioned just is able to copy 1024 items of size T to the kernel stack, which means like 4 kilobytes or 8 kilobytes, depending on the platform, and that's it. So there are a few system calls like that that you can use in both NTOS kernel and Win32k. Yeah.
Cool. Thank you.
Hey, awesome talk. Kind of related, but not. Can you update your awesome function API and CSRSS tables on the blog, or will you be releasing a tool that? Do you do those manually, or do you have a tool to do it? If we want to make our own updates, or?
Yeah, it was done semi-manually, I think, by just copying stuff around from IDA and then parsing it. But yeah, that's definitely something I can do.
Cool.
Yeah.
Thanks.
Sure. Okay, thanks then.